We will be looking at the second chapter, context-free languages. If you remember, I showed this table in the beginning. This is Chomsky hierarchy. So there are 4 types of languages or 4 types of grammars. Each language has a grammar as well as a recognizer or a machine. Machine basically does the recognition job. So you can think of a grammar as the generator and a machine as the recognizer. So a grammar gives you the output, which is the language, and the machine gives you the input, which is the a machine takes the language as input and recognizes it. So finite automaton, what we know as, okay, get out. Yeah, you only get out. No, this fellow is sitting. Yeah, you should have gone to theater. You will get more entertainment there. So, machine, a finite automaton, is basically a recognizer. It recognizes a language, whether it's a valid language or not, whether it's a valid input or not, that kind of thing. Whereas a generator gives you the language. Regular grammars are there, we didn't look at them. Once you look at context-free grammars, it will be easy to understand regular grammars also. So that's why we didn't look at them. We looked at finite automaton. But now in context-free languages, we look at both context-free grammar as well as push-down automata. In push-down automata, there are again 2 variants, deterministic and non-deterministic. Although in finite automata, deterministic variant and non-deterministic variant both are equally powerful, that is not the case in push-down automata. In push-down automata, non-deterministic version is more powerful than the deterministic version, and it is the non-deterministic version which is equivalent to the context-free grammar. The deterministic version is not equal to the context-free grammar. It will capture a subset of context-free grammars. Okay, so that is context-free grammar and non-deterministic push-down automata. And then we have context-sensitive languages, which can be generated using context-sensitive grammars and which can be recognized using linear bounded automata. We will not look at that. We will skip this in this course. We will directly move on to Turing machines, and the languages that can be recognized using Turing machines are called recursively enumerable languages, and the grammars which can be used to generate them are called unrestricted grammars. So whatever a computer can do, that can be captured as a recursively enumerable language, or that can be generated using an unrestricted grammar, or that can be recognized using a Turing machine. Okay, whatever is non-computable is beyond the scope of this table. Whatever is computable will fall in the fourth level. Okay, so as you can see, as you move from top to bottom, the complexity increases and the power increases. Each one of these is a superset of the ones above. Okay, and unrestricted grammar is more powerful than context-sensitive grammar, which in turn is more powerful than context-free, which in turn is more powerful than regular grammar, and so on. Okay, in the first chapter we looked at regular grammars and finite automata. In the second chapter we will look at context-free grammars, context-free languages, push-down automata. Later we'll move on to Turing machine. So this is the overview. We first look at context-free grammars, then context-free languages, then push-down automata, and then there is a pumping lemma for CFLs as well. The way there is a pumping lemma for regular languages, there is a pumping lemma for CFLs as well. We'll look at that at the end. So what are the kinds of problems that context-free grammars can solve? Given an expression like 3 plus 4 into 5, how does the computer know which operation to perform first? I discussed this example with you earlier. Like if you are given an arithmetic expression, how does the computer know to perform multiplication first and not addition? Although addition is coming first in the sequence of from left to right, right? So one logic is, as you move from left to right, whichever operation you get first, just perform that. That can be one logic, but we know that's not how arithmetic operations are run, right? So how do I specify to the computer that don't look at the logic of left to right, but there is a hierarchy of operators, like multiplication and division have a higher precedence than addition and subtraction. You have to follow that order. So how do I tell the computer, irrespective of the order in which you get the symbols, you have to perform the operations in the order of their hierarchy, their precedence? How do I tell that to the computer? That is one issue. Another thing is, like, how does the computer match parentheses in the programming language? This also we sort of discussed. So when you write a programming language, you know there are many matching parentheses that you put, right? If you open some bracket and you don't close the corresponding bracket, the computer will raise a syntax error. Okay, so how does that know? Somewhere some bracket is there, somewhere it is being closed somewhere else, right? So you have a very complex nested sequence of parentheses, but still the computer knows whether they are matching with each other or not, right? So how does that know that? That is not part of regular language. Even if you remember, one of the in the class where we were discussing non-regular languages, I gave you an example and asked you whether this language, imagine a language with all strings, where each string is a string of matching parentheses. So if you have a language with all strings of matching parentheses, is this language regular or not? Some of you said it is regular, but it is a non-regular language, because there is no way in which you can tell whether a string is consisting of matching parentheses or not without storing the opening brackets. You have to keep track of the opening brackets, for which you have to store them. And that is not possible in regular languages because there is no storage apart from the states which you have. So you cannot do it with regular languages. So that is a non-regular language, and basically that is a context-free language. We will see, we will look at the grammar, we will look at the automaton for that, but this is basically a non-regular language. How does the computer know the boundaries of nested for loops or nested if-else conditionals? Again, now sometimes like what happens, if you remember C programming, suppose in your for loop if there is only one line, okay, or if in your if-else condition there is only one line, you don't need to keep brackets, right? And if you have 3 or 4 nested for loops with only one line in the last for loop, even then you don't need to keep brackets, but still it knows where your for loop starts or ends, what falls inside your for loop, what falls outside your for loop, independent of your indentation. If it is C, indentation does not matter in C or C++. In Python, indentation matters. But here, the computer is keeping track of nested for loops, nested if-else conditionals with brackets or without brackets. Again, it needs to keep track of many things. So how does it keep track of that? How does it know that? Again, this cannot be done using regular languages. You need context-free languages for that. And how does the computer know if the syntax of a sentence or an entire program is valid or invalid? Again, this is a context-free language problem. Although your entire program can be thought of as a sentence, every sentence cannot be handled by a regular language. Every sentence is not part of a regular language. There are also, like, imagine a power n, b power n. That is also a word or string or a sentence, but that is not part of regular language, right? So every sentence is not part of regular language. Your program is of the complexity of a power n, b power n. Okay, so it is not part of regular language. It is context-free language. Because in your program, like I said, you need to keep track of matching parentheses, you need to keep track of nested loops like for loop, while loop, if-else conditionals, all these things you need to keep track of, which means you actually have to store them. You cannot just read them and skip them. Even if you take the example of matching parentheses, you cannot just look at an opening bracket and skip it. No, you have to keep track of all the opening brackets so that when you get a closing bracket, you match it with one of the opening brackets. Okay, so this process is not possible using finite automata or regular languages. Fine. So for all these things, the solution is context-free grammars. Okay. So what are context-free grammars and all that? We'll get into the details. So CFGs or context-free grammars can describe languages which are more powerful than regular languages, right? They originated while studying human languages. So Chomsky is said to have found this hierarchy of these grammars. The context-free languages are very close to human languages. Like I'll show you an example of English grammar. It looks very much, it can be captured using context-free language syntax, context-free grammar syntax. Okay. Although Chomsky is said to have founded these different types of grammars or even context-free grammar, at least particularly context-free grammar, later Chomsky himself acknowledged that such a thing actually existed much earlier in Indic tradition. There was philosopher come linguist called Panini. I don't know how many of you heard his name. So he wrote a work called Ashtadhyayi. Ashtadhyayi means 8 chapters. So that was a grammar for Sanskrit, and it is still considered. It is still being used even for computer science. People are trying to apply it to not only Sanskrit but also other spoken languages to formalize them, to make them more easily computable. Okay, so that is a very concise text with just 4,000 rules, and the entire grammar of Sanskrit is given in that. And Chomsky later actually acknowledged that this work was done already, and he basically, people basically came to know of it. The West basically came to know of it after his work, after Chomsky's work. Okay, but now even many foreign scholars work on that. So context-free grammars, they are now also being used to study programming languages and in building a parser. Yeah. I think you get out or you be silent. So they're being used to study programming languages and in building a parser, which is an essential component of any compiler or interpreter for programming language. Like I mentioned earlier, compiler, you know what a compiler is. Whether you're given a C program or C++ program, you compile it saying GCC your file.c, right? It gives you an executable a.o. So this compilation process is not a one-step thing. There are many stages in that. Parser is one part of that. So parsing is done using push-down automaton. Push-down automaton is a part of the compiler. So context-free grammars are used for building push-down automaton. Okay, so I will tell you why we need a grammar and also an automaton later, but it is context-free grammars that actually parse the program you write. No, grammar doesn't parse. It is the push-down automaton that actually parses the program you write, and that is one stage in the compilation process. So this is another use for context-free grammars. Okay, so this is an example of a grammar. So basically there are 3 rules in this. So each one is called a rule, and each rule has a left-hand side and a right-hand side. That left-hand side are LHS and the right-hand side are RHS. So whenever you see the variable, the symbol on the left-hand side, you can replace that symbol with the right-hand side. Okay. So for instance, I see an A here. It can be replaced with the string 0A1. Now within the string again there is an A. Again this A I can replace with 0A1, or I can even replace with B. So I can replace, whenever I see an A, I can either replace it with 0A1 or I can replace it with B. And whenever I see a B, I have only one option. I have to replace it with a hash. Okay, so assume this is my grammar. Now this grammar generates a language. We'll look at all those in a while, but basically a grammar consists of substitution rules or production rules. So whatever 3 rules you saw earlier, they are called production rules or substitution rules because you substitute LHS with RHS. And it also has variables or non-terminals represented by uppercase letters with or without angular brackets. So in this case, capital A, capital B, they are non-terminals, they are variables. The way in a program, in a programming language, you replace a variable with some value. Similarly here, these variables are non-terminals, you replace them with RHS, which is their value. And then terminals represented by lowercase letters. So all lowercase letters, English letters, as well as digits 0 to 9 and any other symbols, which is not a capital letter, is usually a terminal symbol. Okay. So in the previous example, capital A, capital B, these are the only variables, and all the remaining symbols 0, 1, hash, they are terminal symbols. So terminal means the process of generation terminates with them. You cannot proceed further. So when you have a variable, you can replace it with something else. But when you have a terminal, you can't replace it with anything else because there will be no rule with terminal as the LHS. Only when you have a symbol which is an LHS in any one of the rules, you can replace it with its corresponding RHS. Otherwise, you can't replace it, right? And then finally, you have a special variable called the start variable. Like in a finite automaton, you denote some particular state as the start state. Similarly, in a grammar, you denote some particular variable as the special variable, a start variable. Usually, when you write the list of rules, usually the LHS of the first rule is by default considered to be the start variable unless mentioned otherwise. So at least the first rule should be such a way that you want that particular LHS to be the start variable. The remaining rules can be in any order. Okay. So in this particular grammar, so let's call the previous grammar G1. These are the constituents. So the rules are these three are the rules, and variables are capital A, capital B, terminals are 0, 1 hash, and the start variable is A. Okay. For convenience, we can even combine multiple rules with the same LHS using this bar symbol. So for instance, if you see the rules, there are two rules with the same LHS. First rule and second rule. So basically what are they saying? If you see an A, you can replace it with 0A1 or you can replace it with B. Okay. So rather than saying, okay, A can be replaced with 0A1, A can be replaced with B, A can be replaced with something else. So many rules, you can just say A can be replaced with either 0A1 or B or something else or something else. So you can combine all the rules with the same LHS into one rule. So this is how you specify that. This is OR symbol, like you use in programming also. This is the OR symbol, this bar. So if you see an A, it can be either replaced with 0A1 or with B. Okay, or anything else in case there are more rules. But if you see a B, there is only one option. You have to replace it with hash. So there is no other OR rule there. Okay, so we have a grammar. Now let's try to derive a string using this grammar. I want to derive this particular string 000 hash 111. By now, did you understand what kind of language this grammar generates? We can count the other occurrences of, sorry, non-terminal symbols. Okay, fine, that is one answer. Any other answers? Yeah. That's it, or anything more? Okay, anything else? Exactly. Equal number of zeros followed by equal number of ones separated with a hash in between. So it's 0 power n hash 1 power n. It's not arbitrary number of zeros and ones. The number of zeros and number of ones also match. So that you can tell by looking at the rules, right? So A will be replaced with 0 A1. So every time you get a 0, you're also getting a 1. There is no case where you're getting more zeros than ones or more ones than zeros. You're always generating equal number of zeros and ones. Okay, so you will understand how to read a grammar slowly as you practice. So this is an example where 0 cube hash 1 cube. Okay. Now I want to generate this particular string. Now how do I apply the rules? So you start with the start symbol. Okay. Now you have two options. Either you can replace this A with 0A1 or you can replace it with B. Depending on what you choose to replace it with, your end string will change. In this particular case, you have to replace it with only one of the options and the particular option if you want to reach that particular string. You can't replace it with B. Suppose if you replace A with B, then the only option you are left with is to replace B with hash. So you will just get hash. You won't get this string. So for me to get this string, I have to replace A with 0A1. Now I have an A again. I replace this A again with 0A1. I have an A again. I replace this A again with 0A1. Okay. Now for me to get 000 I have to stop here. I replace this A with B and I replace this B with hash. Right? Only then I will get, if I follow this sequence of substitution only, I will get this particular string. If I change this sequence of substitution with any other rule, in any other, at any step, then I'll get a different string. Okay? So whatever I explained, same thing is written here. You write down the start variable. It is a variable on the left hand side of the top rule unless specified otherwise. Find a variable that is written down and a rule that starts with that variable. Replace the written down variable with the right hand side of the rule. So basically, whatever string you are in, find a variable in the string. Once you find a variable, find the rule which has this variable as its LHS. There may be one rule or two rules or 10 rules. Choose one rule, replace this variable with the RHS of that rule. Okay, so there is a rule B goes to hash. So B will be replaced with hash. There is a rule A goes to B. So here A will be replaced with B. There is a rule A goes to 0A1. So here A will be replaced with 0A1. Which rule you choose depends on which string you want to generate. You can choose any rule in any order. Depending on which string you want to generate, you will choose that particular rule. Okay, so look for the variable, find a rule with this variable as its LHS, replace this particular variable with the corresponding RHS from that rule. Okay, that's all. This is the example. This is a parse tree, or one can think of it as a generation tree of the particular string which we discussed. So you start with the start variable. Okay, this can be replaced with 0, A, 1. All right. Now again, this A can be replaced with 0, A, 1. Now again, this A will be replaced with 0, A, 1. This A will be replaced with B. This B will be replaced with hash. So this is how you get a parse tree or a generation tree for a string. Now there are some characteristics of a parse tree. It should satisfy these below requirements. One is all the leaf nodes of the tree are labeled by the terminals of the grammar. Okay, so in the tree, the leaves will all be terminals. There cannot be variables here. There cannot be non-terminals here, because if you have a non-terminal, you have to proceed further. But if you have a terminal, you cannot proceed further because there is no rule with any of these terminals as the LHS. There will be no rule where 0 goes to something, no, or 1 goes to something, no. These will always be part of RHS of any loop. They will never be part of LHS of any loop. Okay, so they can't be replaced with anything. The word terminal itself tells you that it stops here. This branch ends here. This branch cannot proceed further. So it terminates here. Alright, so that's what terminals are. So the leaves of a tree have to be terminals. The root node of the tree is labeled by the start symbol of the grammar. Obviously, here the root node is the start variable of the grammar. You start with the start variable, that is A, and you start replacing it with RHS and RHS and RHS and so on, and you proceed further. The interior nodes are labeled by the non-terminals. Okay, so all the interior nodes here, they are non-terminals. They cannot be terminals. If they are terminals, they cannot be interior nodes. They will be leaves. If they are leaves, they have to be terminals. They can't be non-terminals. And if they are non-terminals, they have to be interior nodes. Okay, that's it. So what is a context-free language? The way we define a regular language. What is a regular language definition? Five tuple. Yeah, a language is said to be a regular language if there is a finite automaton that recognizes it. That is the definition of regular language. So you define a regular language in terms of a finite automaton. Similarly, here we define a context-free language in terms of a context-free grammar. A language is said to be context-free if it is generated by a context-free grammar. That's it. A context-free grammar can generate infinite sentences, potentially infinite sentences. If you make a set of all those potentially infinite sentences, that set is your context-free language. That's all. That's it. That's what this slide is saying. Okay. And this particular grammar which we discussed, that is G1. It can be the language can be represented as L of G1, and this particular language is 0 power n hash 1 power n, where n is greater than or equal to 0. Why is n greater than or equal to 0? Because you can generate even just a single hash without zeros or ones. How? A goes to B, B goes to hash. That's it. Okay. Again, formal definition of context-free grammar. It is a 4 tuple V sigma R S where V is a finite set called the variables. Sigma is a finite set disjoint from V, separate from V, called the terminals. So terminals are different, non-terminals are different, or variables are different. R is a finite set of rules, with each rule being a variable and a string of variables and terminals like LHS and RHS. RHS can be, it can be a mix of variables and non-variables, whereas LHS is always a variable. And S is the start variable. One of the variables from the variable set is denoted as the start variable. Okay, like in finite automata, one of the states from the set of states is denoted as the start state. Similarly, one of the variables from the set of variables is denoted as the start variable. Okay. So in the previous grammar, these are the components. So the set of variables, that is AB, set of non-variables or terminals, that is 0, 1, hash. You can also think of it as the alphabet set for the language. So finally, language will consist of strings made up of only sigma. They will not consist of strings made up of ABs, capital A, capital B. Those will not be part of the language. Language will only have strings made up of zeros and ones and hash. That's it. And R is the set of rules. These three rules constitute R, the rules in the grammar, and start variable is A. Okay. Again, the formal definition of derivation. If you remember, while discussing formal automata, finite automata, every time we defined a finite automaton, we also gave the formal definition for computation of that automaton. Once we defined DFA, we gave formal definition of computation for DFA. When we defined NFA, we gave formal definition of computation for NFA. When we defined GNFA, again we gave a formal definition of computation for GNFA. Similarly, here we defined a context-free grammar. Now we are also defining when a string is said to be generated by a context-free grammar. So we are formally defining generation or derivation of a particular string using a grammar. Okay. So if U, V, and W are strings of variables and terminals, and A goes to W is a rule of the grammar, we say that UAV yields UWV, written UAV like this. Derives in the sense, in this case it is yields. I will tell you the difference between yields and derives just in a minute. UAV yields UWV, that's how we say that. We say that U derives V, written U, this symbol, star V, if U equal to V, or if a sequence U1, U2 and so on UK exists for k greater than or equal to 0 such that U yields U1, U1 yields U2 and so on, you get UK, and finally UK yields V. Okay, so by now I believe you understand the difference between yielding and deriving. What is the difference? Yeah. Yeah. Basically, when you go from one string to another string in exactly one step, that is yielding. This string yields this string. Okay. Whereas if you can go from one string to the other string in 0 or more steps, that is deriving. That's it. So you can derive V from U if you can go from U to V in 0 or more steps. Whereas you can yield V from U if you can go from U to V in exactly one step. That's the only difference. Okay, so star, again, same meaning, 0 or more steps. You can derive V from U if you can go from U to V in 0 or more steps. Okay. Formal definition of the language of the grammar. So we defined what is a context-free language. Now same thing, earlier we just gave a verbal definition, now we are giving a formal definition. So the language of the grammar G with star symbol S and the set of terminals sigma is, so the language of the grammar is set of all those strings. W belongs to sigma star means W is a string, right? Sigma means alphabet, but W belonging to sigma star means string. So set of all those strings such that the string is derivable from the start symbol of the grammar in 0 or more steps. So all the strings that are derivable by the grammar from the start symbol in 0 or more steps, the set of all those strings constitute the language of the grammar. Okay, another way of putting it is the language of G is again W belonging to sigma star such that there exists at least one parse tree for W. This is another way of saying that W can be derived using grammar G. In the previous case, you see, we have a parse tree for this string 000 hash 111. Now, how did we get this parse tree? It's because we are able to apply the rules according to the grammar G1. Otherwise, we can't get this parse tree. By following the rules of a particular grammar, if you can get a parse tree for any particular string, then that string is said to be generated by the grammar. Now, no matter how much you try, you can't get a parse tree for a string like say 0 hash 11. You can't get a parse tree for that using this grammar, which means 0 hash 11 is not derivable using this grammar. Okay, so if a string is derivable using a grammar, there will be a parse tree for that. This is another way of saying W belongs to the language of the grammar G. Okay. So there are two different ways. Either W can be derived from the start symbol of the grammar, or W will have a parse tree. That's it. Any which way is fine. Okay, so this is the example for English which I was speaking of. So English, natural language English also has a grammar. Now, so first let's look at the grammar and then I'll explain some other things. So any sentence you take in English, basically we say sentence has a grammar, right? Usually you would have heard of like subject, verb, object, that kind of sequence, right? But slightly more formal grammar looks like this. So any sentence you take, it has a grammar. So how does the grammar look like? The sentence will have noun phrase and a verb phrase. Noun phrase can be either a complex noun or a complex noun followed by a preposition phrase. Now these are the variables in my grammar. Since there is more than one letter in each word, they are put in angular brackets. Okay, that's the only difference. But capital letters, whatever are written in capital letters, those are variables. They are not non-variables. You cannot end your string with these variables. They have to be replaced with some terminal symbols at the end. Okay. So each one of these needs to be expanded later. Each one of these will need to be part of an LHS. There should be a rule with each of these variables as an LHS. Okay. So noun phrase can be either a complex noun or a complex noun followed by a preposition phrase. A verb phrase can be either a complex verb or a complex verb followed by a preposition phrase. A preposition phrase is a preposition followed by a complex noun, and a complex noun is an article followed by a noun. A complex verb is either a verb or a verb followed by a noun phrase. Now, again, articles, we took a very limited set of words from English, a very, very small set of words, and we can generate still infinite sentences using only these words. Okay? So, we took only two articles, A and B, and noun, only three nouns we take, boy, girl, flower, and verb, we take only three verbs, touches, likes, sees, and preposition, we take only one preposition, with. Now, this entire grammar is actually English language grammar only. If only you take all possible articles, all possible nouns, all possible verbs, all possible prepositions in the dictionary of English, you will get entire English language using this grammar. Okay? But this grammar, not only this grammar, for any natural language, the grammars we have, they are not comprehensive grammars. They are not extensive grammars in the sense every possible sentence in English cannot be captured using this grammar. You can still generate some sentences in English which cannot be captured using this grammar. At the same time, this grammar will generate some sentences which are not in English. Okay, but mostly this is an approximate grammar, you can say. In fact, for any natural language, you cannot come up with an exact grammar because natural languages are open-ended. Normal sentences themselves are open-ended, and if you imagine if you venture into poetry, that is much more complex. You can't come up with, this grammar will not capture any poetic sentences, right? But in general, most of the sentences, basic sentences, follow the structure. Okay, that is the reason we had to come up with separate languages called programming languages to deal with computers. We can't use natural languages because they are open-ended and their meanings are not clear, right? In programming languages also we have grammars. That's what we are seeing, context-free grammars and all that. They are grammars for programming languages. They are more neat, more concise, more closed. Okay, even these grammars, programming languages grammars are complex enough that their formal properties are not yet proved. Formal properties like completeness or soundness, those kind of properties are not actually proved. They work. Okay, still one can imagine, probably, maybe we are unable to imagine a scenario where they will fail, but there can be scenarios where they will fail. But they are still better compared to natural languages because they are defined by us. Their meanings are defined by us. Their limitations are defined by us in that sense. Okay, natural languages have no limitations, right? Anyway, so given this grammar, let's try to, so first let's look at the details of this grammar. So this grammar has 10 variables, like each one of these is a variable. So there are 10 different variables and 27 terminals. This is made up of English letters only, but we will not go to the level of each letter. We will stop with these words. Okay, we will stop with these words. These words, we will consider them as our terminals. The moment we see these words, we will stop generation because they are not part of, they are not LHS of any loop. We will stop them. Okay, so we are taking words as our terminals, although technically letters are terminals, but for the time being, we'll consider words as terminals. And then 18 rules are there. How you need to actually break down each of these as 2 rules. Every time you have an OR condition, that should be counted as an extra rule. Okay, so totally there are 18 rules. So these are some example sentences that can be generated using this grammar, like a boy sees, or the flower sees the boy likes a girl with a flower, a girl likes a boy, a flower likes a girl with a flower, a boy sees a girl with a flower, likes a boy with a boy. All kinds of sentences you can generate. Some are meaningful, some are meaningless, but they can be generated. Okay, I think I also gave you, probably I would have given you this example, like colorless dreams sleep furiously, something like that. Now this sentence is a valid sentence, not in terms of the meaning, but in terms of the syntax. Okay, why? Because I'll give you another sentence, like maybe the tall boy runs quickly. In both these cases, the order of the parts of speech is fine. Like tall boy runs quickly. Adjective, noun, verb, adverb. Proper sentence, perfect sentence. Similarly, colorless dreams sleep furiously. Adjective, noun, verb, adverb. Okay, so syntactically, both sentences are valid. You haven't disturbed the order of the parts of speech, but the values of parts of speech that you replaced this with, that is making the sentence slightly counterintuitive or not making much sense, right? Like, what do you mean when you say dreams are colorless? And what do you mean when you say dreams are sleeping? And what do you mean when you say sleeping furiously? None of these are sitting well with each other, right? So that is the issue, because the grammar which I even showed you just now, it is a grammar only for the syntax of English, not for the semantics of English. Even the programming languages which we have, their grammars are for the syntax of the programming languages, not for the semantics. Okay? So you can get syntactically valid sentences, but semantically invalid sentences. So far, no grammar has been developed for the semantics of any language. It is difficult. It's not possible. Even in programming languages, you have something called operator overloading, right? For instance, if I say A plus B, now this plus may mean addition if A and B are numbers, or it may mean concatenation if A and B are strings. Like if you take Python, this is what plus means. All right. But what if one of them is a string and another is a number? Now, how do you handle the situation? Do you convert the number also to a string and concatenate it with the original other string? Or if the string, say it has only one character, do you convert this character to a number and add it to the number? Right? These are all semantic issues. They are not syntactic issues. Again, semantic issues like division by 0. there is a semantic error. You can't divide using a 0. But when you write A by B, it will not raise any error because it doesn't know what is the value of B beforehand. Only when the user gives the input, only then it will know. So it can't raise a syntactic error. There is no syntactic error there. A by B, perfectly valid expression. But it becomes a semantic error when your input, when your denominator is 0, right? So there can be semantic errors also, and you can't handle every semantic case using grammar. First of all, you cannot write a grammar for semantics. Okay? So either it's a natural language or it's a programming language. The grammars which we have are only syntactic grammars. They are for syntax. That's it. The only advantage we have is because syntax in programming languages we have one-to-one semantics. Each symbol, one meaning. That is the reason. But in language, each symbol can have different meaning. Depending on the context, the meaning may change, right? Or each word may have multiple meanings. I think I mentioned this also maybe a couple of times, like in English or any natural language, you have synonymy problem and polysemy problem. One word may have more than one meaning, or more than one word can have the same meaning, right? Because of this, the context, the meaning will change, right? Like you can say, I'm going to the bank. Is it the river bank or the financial institution? It depends on the context, right? So same word, different meanings, and so on. So it is not a syntax problem, it is semantic problem, but that's a more complex thing. Right now, syntactic grammars are more than enough to do the job for us, okay? Okay, so we look at the derivation of one particular string. You see there are two things. One is a set of rules, okay? Here you see the arrow is, it looks like this, single line, okay? Now using these rules, you can generate different kinds of sentences. Now each sentence, you need to follow some steps to generate that sentence. Like in the previous example, this is an example of derivation of the sentence. This particular sentence, you are deriving step by step using the rules, okay? In any order you want. Whereas this is the set of rules. So there are set of rules, and then there are a sequence of steps in which you can apply the rules from the grammar in any order you want to generate a particular string. Okay, so don't confuse the two. Derivation arrow, this is arrow in the rules. This is arrow for derivation. So whenever you see this, understand it's a derivation, it's not a rule. Whenever you see the other arrow, understand it's a rule, it's not a derivation. Okay. Similarly, this is a grammar. These are rules. You are not deriving anything here. You are just specifying the rules of the grammar. Now, using these rules, you will derive some particular sentence. You need not use all the rules in the given order. You can use any rule in any order, any number of times to derive one particular string. Okay. Now, these are all different strings that can be generated using the previous grammar. We will take the first string and show the derivation, the step-by-step derivation for that particular string using the rules from the grammar. Okay, so this is the string I want to derive. So you start with sentence. Now you need to apply the rules in one particular order so that you will finally land up in this string only. Okay, so you need to basically break down this sentence into noun phrase and verb phrase. Okay, noun phrase is a boy, verb phrase is sees. Okay, now noun phrase again you break it into complex noun followed by a verb phrase. So you need to apply the rules. Noun phrase will be replaced with complex noun. And then complex noun will be replaced with article and noun. Okay, and article will be replaced with a. And then noun will be replaced with boy, and then verb phrase will be replaced with complex verb. Complex verb will be replaced with verb. Verb will be replaced with sees. Okay, so if you want to get this particular string, you have to follow this particular order. Okay, and those particular rules you need to apply. Okay, so this example, I discussed this language example, I didn't discuss the grammar. If you remember the lecture on non-regular languages, one of the examples that I discussed was, again, I mentioned it just a while ago, right? Matching parenthesis. So is the language where each string has matching parentheses, is that a regular language or not? It is not a regular language because the only way in which you can build a machine which recognizes, which accepts these kind of strings is by storing all the opening parentheses. Like in a stack, right? You store all the opening parentheses in a stack. Every time you get a closing bracket, you pop the top opening bracket. Again, if you get a closing bracket, you push it onto the stack. Once you get an opening bracket, you pop the, once you get a closing bracket, you pop the opening bracket from the stack. So if you continue this process, by the time you finish reading the string, if your stack is empty, then your brackets are matching. That is a valid string. Otherwise, that's not a valid string. So in this, the important thing is you need to store all the opening brackets. You need some storage. That storage is not allowed in regular languages, is not allowed in finite automata. Okay, so that is not a regular language. The moment you bring in storage, it is not a regular language. Okay, context-free languages can do that because push-down automata allows you for storage. You can store the opening brackets in a stack, and when you get a closing bracket, you can pop the top element from the stack. Okay, so this is possible. Storage is possible in context-free languages. So this is a context-free language. This is not a regular language. All right, and this is the grammar which actually generates this particular language, like ASB and SS or epsilon. So S goes to ASB, or S goes to SS, or S goes to epsilon. So what do we mean by that? The way, if you remember, the way I told you, every state in a finite automaton can be given a meaning, right? Similarly, every variable in a grammar can be given a meaning. Now, if you think of S as a string of matching parentheses, imagine I already gave you a string with matching parentheses. Now, using this string, how do you build larger strings of matching parentheses? There are basically two ways. One is you take this string, you add another pair of brackets around this to construct a larger string of matching parentheses. That is one way. Another way is you take one pair of matching parentheses, one string of matching parentheses, another string of matching parentheses, and concatenate them to form a larger string of matching parentheses. These are the only two ways. Is there a third way? No. You can try thinking, but there is no third way. Whatever complex way you think of, that can be broken down into these two ways. Okay? So that's what is happening here in this grammar. So if you assume S is my string of matching parentheses, I can build larger string over it by adding a left and right bracket. You can think of A and B as left and right brackets, or you can take one matching parenthesis string and concatenate it with another matching parenthesis string and build a larger string. So that is what is being said in these two rules, ASB and SS. And for you to terminate this process, you have to replace S with epsilon. Otherwise, there is no rule where S is being terminated, right? You have to have some terminal rule with S being replaced with epsilon. So this is allowing you to accept even an empty string. So that is also fine because you have 0 opening brackets, 0 closing brackets. That is still same number of opening and closing brackets. So that is also some kind of matching parenthesis. Suppose if you want minimum one pair of brackets, then instead of epsilon, what should you write? That's all. S goes to AB. Instead of epsilon, S goes to AB. So let me quickly show you an example of matching parenthesis. Yeah. I will show you the, oh, this one, this S in brackets, this thing you are asking. Yeah, this is the formal definition of the grammar. That is the set of variables, set of terminal symbols, set of rules, and the start variable. So set of variables, here there is only one variable, but still it is a set. So you have to represent it in set. Set of terminals, AB. Okay. So yeah. Let me quickly show you an example. No, epsilon is never part of the alphabet set. Like I said in finite automata, same thing here. Epsilon is not a special symbol. Actually, it's a special symbol. It's not a regular symbol for it to be part of a set. Like this set will have epsilon, this set will not have epsilon. No. grammars are allowed to use empty string. That's all. Okay. Suppose you want to generate this pair of parentheses. Okay, basically let me modify this grammar slightly. The grammar we saw, let me modify it slightly, like S goes to capital ASB or SS or epsilon, and capital A goes to left bracket, capital B goes to right bracket. Same grammar, I modified it slightly. Okay, now suppose I want to generate this pair of parentheses. Now I start with S. I have two options, ASB or SS. Which rule should I apply? You look at the nature of the string you have. Is it of the nature that you have a string which is increased by adding a pair of parentheses around it, or you have one string of matching brackets followed by another string of matching brackets? Is the second option, right? Second case. So S should go to SS. Okay, which means this is an S and this is an S. Now this S, again, what is the scenario? Is it ASB or SS? This is ASB. ASB. Again, ASB. And this A goes to left bracket, this B goes to right bracket. These are the only options. That will always be the case. Okay. And this S will go to epsilon. Again, left bracket, epsilon, right bracket. Okay. So now you just look at the leaves. They will match with the string. Okay. So let me take one more example. Now this, what is this? Is it of the nature you have a string with another pair of brackets around it, or one string concatenated with another string? First scenario, right? You have a string where there is a pair of brackets around it. So this is of the form ASB. This will be left bracket, this will be right bracket. Now again, this S is of the form ASB. This is left bracket, epsilon, right bracket. So you trace the leaves, you will get this string. One last quick example. What about this one? I should start with, is this, yeah, this is SS, right? This is one string, this is another string. So SS, you can think of it as S1 and S2. Now S1 is of the form ASB, S2 is of the form ASB. Okay, so this will go to ASB. Again, this will go to ASB. And again, this A will be left bracket, B will be right bracket. This S will again go ASB, right? This will be left bracket, right bracket, epsilon. This will be left bracket, epsilon, right bracket. Now you can even number these. Say this is 1, 2, 3, 4, 5, 6. That's how these will 1, 2, 3, 4, 5, 6. Okay, so these symbols have meanings. Don't look at them just as symbols. Okay, by looking at the structure of the string, you should say whether it is of the form SS or ASB, right? So that's how you choose from the top level. How do you know which rule to apply? You know, there is a huge gap. There are many steps between the top start variable and the end variable, right? Start variable and the end string. How do you know which rule to apply? So you should have a broad view of the rules to apply, because that can be possible only when you give a meaning to each variable. Okay, so let's stop here. Let me take attendance.